Good evening, ladies and gentlemen. First of all, thank you for your patience, for waiting for the latest presentations. I'm going to be brief, but not shallow, even if we deal with a shallow geothermal system here. So this is, no, okay, no, I should go. What? No, I want to go backwards. The smaller one? Okay, yes. Yes, this is the first slide I wanted to present. So this is an overview of my whole presentation. I will make a short introduction. I will show the input data, the simulations results provided by the EED software, which is Earth Energy Designer for the initially designed situation, then the optimized situation from functional point of view, conclusions, and then I will end with some information about a center of excellence for shallow geothermal energy. So the whole story began when a company asked us to provide some consultancy with regard to a technical project. It was an industrial investment in a dairy factory. So the investor received some funds for providing heating for his industrial application by means of ground source heat pumps. So the data that were available at that moment consisted in the output of the heat pump, which was 200 kilowatt. He had money for 40 boreholes, 90 meters deep each. And he had a project for heating, sanitary installations, but it was no coordination with the geothermal system. We had some other supplementary information regarding the hydrogeological study, which was quite important for the parameters of the underground, the geotechnical study, and as I said, the technical project for the HVAC sanitary and pipeline networks. So what we did was a simulation of the geothermal system by means of the input data that were provided by the investor. And we made some, let's say, common sense assumptions regarding the use of the heat pump for heating and production of domestic hot water. These are the data that we provided to the software. These are typical data. And something very interesting, and we had to set this data, was about the heating fluid. And we chose as heating fluid flowing through the borehole heat exchanger a solution of ethylene glycol, water, with a pretty low solidification temperature of minus 21 degrees Celsius. And we calculated the heating energy for 1 year by using the red screen ASHRAE method, using the temperature bins and the heating curve provided by these 200 kilowatt. And also we calculated the domestic heat water energy for 1 year. And these are the data that we had to feed to the software. Now these are the results that EED provides. The energy consumption, the heating energy base load, and then the heating energy peak load, and these are the results that EED provides. Basically, it provides the temperature, the average temperature of the fluid for base heating load during 1 year and during 15 years of functioning of the system. And the graph is, well, difficult to read. You can see the, let's say, the structure of the graph with a minimum at the beginning and at the end of the year. And here you can see the minimum and maximal fluid temperature for the base heating load during 15 years of functioning. And as you can see, these temperatures are dropping during 15 years. This is very bad because the system is heating only. So that means that the underground is depleted from heat and has no other source of replenishing other than the natural heat flux coming from the surroundings. Now, after a first simulation, we found out very disturbing information, namely the fluid minimum average temperature is minus 12 degrees Celsius for the base heating load and minus 17 degrees Celsius for the peak heating load. That means that at these temperatures, the fluid flowing through the ground source heat exchanger becomes very viscous, has a high viscosity. That means that the pumping energy will be very, very high. And also, because of the temperature drop, the COP of the heat pump will drop considerably. Now, the conclusion is that the length of the boreholes, which is only 90 meters, cannot cover the energy needs for the heat pump in order to make it function properly. So what we did, we imposed some technical conditions, and we set the minimal temperature of the fluid to minus 5 degrees Celsius, which is quite decent. And we repeated the calculus for this imposed temperature. And of course, we maintained all the other technical data that we fed the software to. All the ground properties, the configuration of the ground source heat exchanger, and also the energy data, the heating base load and the heating peak load. And the results are, let's say, as you can see as a form, the graphs are very similar. Of course, the temperature drops during 15 years of functioning. And in this table, you can see the conclusions of our analysis. On the column in the middle, we can see the values for the initially designed situation with very low temperatures for the fluid in the base heating load, in the peak heating load. And the number of boreholes was set to 40. And what is very important, the depth of the borehole was set to 90. In order to have a minimal temperature of minus 5 degrees Celsius for the peak heating load, we need 161 meters depth for the boreholes. That means the boreholes need to be much deeper in order to be able to cover the energy needs for the heat pump. And that means a terrible increase in the investment for drilling. So these are the, let's say, final conclusions of this analysis. It shows that faulty design of the ground source heat pump system may lead to totally inefficient functioning of the heat pump, low evaporation temperatures, low SPFs, and a possible optimization from technological point of view may lead to increased costs for the borehole heat exchangers by more than 70%. So it is very, very important when designing ground source heat pump systems to make a thorough calculation and, of course, to harmonize all engineers dealing with the energy systems in that facility, be it building or industrial facility. Now, I would like to go to the last point of my presentation. I'm going to speak about the Center of Excellence for Shallow Geothermal Energy. The participation of the Romanian Geoexchange Society for the last 4 years in European projects made us possible to reach this, let's say, hope, because in the last project in which we are involved, which is called Geo4Civic, we are about to establish a Center of Excellence for Shallow Geothermal Energy in our faculty for Building Services Engineering, Bucharest. And that means that we have a headquarter. We have, as infrastructure, we have also 2 nearly zero energy building houses for demonstration purposes. And last week we finalized an experimental W borehole heat exchanger, 100 meters deep, and it is documented with 21 points for temperature measurements along the borehole. And we have some, we have also another system in our faculty, which can be also used for, let's say, teaching purposes and demonstration purposes. We have an underfloor heating system provided with a ground source heat pump system. These are the 2 houses I was speaking about. They were participating in the solar decathlon competition. The first one is already in place, the one on the left-hand side. And the house on the right-hand side has been brought to our faculty, and last week they finished the structure. We also have a mobile geothermal laboratory with a GeoCube for thermal response tests. And also we finished last week a TRT for a thermal pile system in Romexpo in Bucharest. So I'm very glad for all our activity, and we have a lot of work to do ahead of us. Thank you for your attention.